What I'd like to do next is talk about what we're going to actually infer, what we're going to actually try to learn after running a simple linear regression. In order to do that, I first want to think back to how we thought about one-sample t-tests and what we did in that simpler context. So the idea we had with one-sample t-tests was that we could take advantage of the central limit theorem to say that our estimate of the mean, x bar, will follow a normal distribution centered at the true population mean with variance sigma squared over n. So this is the statement of the central limit theorem that we used. Then what did we do with this? Well, we pointed out that you could take x bar minus mu and divide by the square root of sigma squared over n, and that should follow a normal distribution with mean 0 and variance 1. Okay? And we also said that if we substitute an s for the sigma, if we have x bar minus mu divided by the square root of s squared over n, that should follow a t distribution with n minus 1 degrees of freedom. So we used this for our hypothesis test, right? We said, let's calculate this test statistic and compare it to this distribution in order to get a p-value. The other thing we did was we created confidence intervals. So we said, all right, let's take x bar plus or minus the cutoff from the t distribution, which is approximately equal to 2, times square root of s squared over n, with the idea that the probability that this interval, and I'll just do it in words, includes mu is equal to 0.95. The probability that mu is within this range should be approximately 0.95. This is what we did in the context of a one-sample t-test. And I'm running this down here so that we can make it parallel to what we're going to try to do to learn from a simple linear regression. Remember that the idea here is that if we were to do a simulation, if we really had a normal distribution with mean mu and variance sigma squared, and we sampled from that and wrote down x bar, and we did that sampling and that writing down of x bar repeatedly, 10,000 times, the histogram we'd end up with would look normal with mean mu and variance sigma squared over n. So we're going to make a parallel statement now about the regression coefficients. Unlike in the simple one-sample t-test, where we're sampling values from one normal distribution, in the simple regression context, we have to think about sampling values from some true regression model. So the idea is there's some true value of beta 0, some true intercept. There's some true value that the mean of y goes up by when x goes up by 1. There's some true slope. And the way we're going to sample is we're going to pick some x's, not even randomly. It doesn't have to be random. We're going to arbitrarily pick some x's. And for each value of x, we'll find the point on the line. And that represents the mean of y given that x. And then we're going to draw from a normal distribution centered at that point on the line, centered at that mean of y, with variance that we'll call sigma squared. The way to do this with some software to do the simulation is to pick the x's and then take those x's, plug them into the line, so beta 0 plus beta 1 x, and then add some normal error. Add some error from a normal distribution with mean 0 and variance sigma squared. And we have to pick beta 0, beta 1, and sigma squared. And then what we end up with is a data set that contains a bunch of x's, which are arbitrarily chosen, and y values that were sampled from normal distributions centered at the line given x. The idea is that just like I can repeatedly sample from a normal distribution in the one-sample t-test context, I can repeatedly sample values of y that go along with this line. So if this is the true line, and these are the x's I've chosen, one sample might look like this. And let me erase this so it's easier to see. If this is the true line, and these are the x's I've chosen, one particular sample of y's might look like this, right? And I could try to fit a line to those data points, and it would be similar but not exactly equal to this true line that I've drawn. If I do it again, if I again pick the same x's and sample y's by taking the line and adding or subtracting some normal error, I will get a slightly different data set. And if I take that data set and estimate the intercept and slope, I'll again get a line that'll be a little bit different from the true line. So just like in the simple one-sample t-test context, we were talking about sampling from a normal distribution and then writing down x bar, now we're talking about sampling values that are a little bit above or below this line, y values that go along with x's, and repeatedly estimating the intercept and slope that we would obtain. And the idea is just like x bar will be a little bit different for each sample that we can obtain, beta 0 hat and beta 1 hat can be a little bit different for each sample that we could obtain. And in fact, it turns out that if we were to do this simulation, both of them would follow a normal distribution. So the set of 1,000 slope estimates that I could generate from 1,000 different samples would follow a normal distribution. The set of 1,000 different intercept estimates that I could generate from 1,000 different samples would follow a normal distribution. And each of these would follow a normal distribution centered around the corresponding true value, the true intercept, or the true slope. Because each of these quantities is unbiased, which is exactly means what I just said, that on average it would be equal to the truth. Okay? And each of these would be normal with some particular variance that I'm not going to write down yet. Some particular variance. So I can go through this process for the beta 0 hat, and I can go through this process for the beta 1 hat. Because we're more interested in the slope, let me erase this to give myself room and focus on the slope. Although we could do the same thing for the intercept.